Hi, good morning to all. Today we discuss about discrete time Fourier transform. In short, we can say that Dtft. Here we consider an aperiodic discrete time signal, that is x of n, and it is a finite duration sequence, and its Dtft can be expressed as x of e raised to j omega equal to summation over n varies from minus infinity to plus infinity x of n e raised to minus j omega n, and this is known as analysis equation. And its inverse, it can be computed by x of n is equal to 1 by 2 pi integral over 2 pi x of e raised to j omega into e raised to j omega n d omega, and it is known as synthesis equation. When we check both these equations, that is Dtft and inverse Dtft equation, otherwise we can say that analysis and synthesis equation, it is clear that these are not symmetric. When we check the analysis equation, here we use the summation. In the case of synthesis equation, we go for integration over 2 pi. What is the reason for that? We know that the input signal x of n, it is in a discrete time signal. That's why we go for summation of infinite times. Whereas in the inverse Dtft, that is in the synthesis equation, here x of e raised to j omega, it is in the frequency domain and it is continuous. It is continuous in frequency domain. That's why we go for integration over 2 pi. So it is clear that x of n, it is a discrete in time domain. When we compute the Dtft, that is its a Fourier transform x of e raised to j omega, it is continuous in frequency domain. And one more thing, the Dtft, it is periodic with period 2 pi. The Dtft is periodic with period 2 pi. We can say that x of e raised to j omega equal to modulus of x of e raised to j omega into e raised to j theta of omega, where theta of omega is the argument of x of e raised to j omega. Omega is the frequency, where modulus of x of e raised to j omega is called the magnitude function and theta of omega is called the phase function. Here both these quantities are real functions of omega. In many applications, the Dtft is called the Fourier spectrum. So we can say that modulus of x of e raised to j omega as the magnitude spectra and theta of omega as the phase spectra. We can't find the Dtft for every aperiodic sequence. The reason is that in order to find the Dtft, the sequence must satisfy some condition, that is the signal x of n, it is absolutely summable. In mathematically we can express it as summation over n varies from minus infinity to infinity plus infinity, modulus of x of n, it must be less than infinity. Then only we can compute the Dtft of the particular sequence x of n. We can check some examples starting with unit pulse and unit step. We know that the unit pulse, that is a del of n, it is a non-zero at n is equal to 0. That is at the origin it have non-zero value. If we compute its a Dtft, you can substitute del of n at the position of x of n and it is non-zero only at n is equal to 0. So you will get the value 1. And we can compute its magnitude and phase. We know the equation x of e raised to j omega, it can be expressed as modulus of x of e raised to j omega and e raised to j theta of omega. Here modulus of x of e raised to j omega is a magnitude term and theta of omega is a phase. When we check with this equation, x of e raised to j omega equal to 1, that means its magnitude is 1 and the phase is 0. When we plot its a spectra, so we can plot the x of e raised to j omega, its value is 1 and it is ranges from minus pi to pi. What is the reason? We know that the Dtft, it is periodic with period 2 pi. Here we consider 2 pi, that's why we take the ranges from minus pi to pi. That means the spectrum is constant and it is periodic over the range minus pi to pi. Next we consider its shifted version. That is del of n minus n0. So it is clear that it have non-zero value only at n is equal to n0. So you can substitute that shifted unit pulse at the place of x of n. So the equation becomes summation over n del of n minus n0 into e raised to minus j omega n. It have non-zero value only at n is equal to n0. So substitute that here. So this equation become e raised to minus j omega n0. Here also we can compute its magnitude and phase. So modulus of x of e raised to j omega is modulus of e raised to minus j omega n0. We know that modulus of e raised to minus j theta is 1. So here modulus of e raised to minus j omega n0 equal to 1. And the phase angle x of e raised to j omega equal to angle of e raised to minus j omega n0. And here when we compare with this equation, we know that theta of omega is omega into minus omega into n0. Okay, so the magnitude is 1 and the phase is minus omega n0. So compare with the unit pulse, it is clear that the magnitude is same, only the difference in the phase term only. So the shift in the time domain, it will result a linear shift proportional to omega in the phase term. And when we plot its spectra, it is clear that it is also periodic over the range minus pi to pi. Next we consider an unit step. When we take the Dtft of unit step, we know that u of n, it is not a time limited function. So based on the existence of Dtft, it is clear that there is no Dtft in the ordinary case. So unit step have no Dtft normally. Next we discuss about exponential decaying signal. Consider an exponentially decaying signal. X of n is equal to a raised to n u of n, where mod a less than 1. Here when a greater than 0 and a less than 0, you will get two different types of signal. First of all, we can find its Dtft. For that, a raised to n u of n, it is a signal. It have the ranges from 0 to infinity and its magnitude is decided by a raised to n. So you can substitute that in the equation. So summation over n varies from minus infinity to infinity, x of n e raised to minus j omega n, where x of n is a raised to n into u of n. It is a signal from 0 to infinity and its magnitude is decided by a raised to n. Then we can rewrite it as summation over n a into e raised to minus j omega whole raised to n. Here you can use the identity summation over n varies from 0 to infinity x raised to n, that is equal to 1 by 1 minus x if mod x is less than 1. Here we can say that modulus of a into e raised to minus j omega is less than 1. So you can substitute this identity here. You will get 1 by 1 minus a into e raised to minus j omega. This is the Dtft of the exponentially decaying signal. Next we can check its spectrum. First we find its magnitude. So modulus of x of e raised to j omega, that is equal to modulus of 1 by 1 minus a into e raised to minus j omega. We know that e raised to minus j theta is cos theta minus j sin theta. So substitute that here. You will get an equation like this one. And we can rearrange. Here it is a modulus of a complex number. So you will get 1 by square root of real part square plus imaginary part square. That is 1 by square root of 1 minus a cos omega the whole square plus a sin omega the whole square. And we can simplify this equation further. Here it is in the form of this equation. The first term 1 minus a into cos omega the whole square, it is similar to a minus b the whole square form. So you can expand like this. a square minus 2ab plus b square. So that is expanded here. And in this equation, a square cos square omega plus a square sin square omega. You can take a square outside. So you will get cos square omega plus sin square omega. It is 1. So the equation reduces to 1 minus 2a cos omega plus a square. So you will get the magnitude as 1 by square root of 1 minus 2a cos omega plus a square. Next we check the spectrum of the exponentially decaying signal. We put the two values omega is equal to 0 and omega is equal to pi, the magnitude response. So you will get the equation as at omega is equal to 0, the equation will be 1 by 1 minus a. At omega is equal to pi, you will get the equation as 1 by 1 plus a. I already said that we have two different input signal based on the value of a. If a is greater than 0 and a less than 0, we have two different signal. The same way the spectrum is different. We can check that when a greater than 0, at omega is equal to 0, the equation is 1 by 1 minus a. A greater than 0 means the denominator term will be lesser. So the magnitude will be higher at omega is equal to 0. When a greater than 0, at omega is equal to pi, the denominator term will be higher. So the magnitude at omega is equal to pi will be lesser. So when we plot the spectrum, you will get a low pass filter like this one. It is a low pass filter. It have maximum value at omega is equal to 0. It have minimum value at omega is equal to pi. If we check a less than 0, what is the case? A less than 0 at omega is equal to 0. What happened? The denominator will be higher. That means magnitude will be lesser at omega is equal to 0. When a less than 0, the denominator will be lesser. So the magnitude at omega is equal to pi will be higher. So when we plot that spectrum, you will get an high pass filter like this one. Okay, consider from 0 to pi. At 0 we have minimum value. At pi we have maximum value. Thank you.